Ich freue mich, dass ich heute was zum Thema Real Driving.
I'm really pleased that I can talk to you today about real driving emissions. Now, it's a rather interesting topic.
Mehrtägige Konferenzen damit gefüllt.
Some people spent whole conferences talking about nothing else but that. So it's my task now to condense all of that into 20 minutes. So I beg your apologies if I have to skim over this information quite fast.
Ich würde starten mit einer ganz kurzen Einleitung.
So I'll start by giving you a brief introduction on RDE, real driving emissions. Most of you will know what it is about anyway. I'm going to address the challenges as we see them because of the new legislation that's come in. And then I'm going to transition to the question why looking at efficiencies in front loading is so important in the context of RDE. And finally, I'm going to present a couple of examples on methodological approaches and tools. Now, let me just briefly show you what will change with RDE. Now, it's been in effect in Europe since the 1st of September, this new legislation, and it includes some new things. One is the cycle, which is performed on the dyno, or the chassis test cycle. It's now been replaced by the real driving emissions cycle, which is far more dynamic. And in addition, also, cars will have to be certified on the road too as part of an RDE test. And there's no specific cycle requirements, but it has to be carried out in a broader context. So there are greater degrees of freedom here, and that is going to be the main challenge, as we said. Now, this, of course, affects, of course, the dynamic conditions, but also the ambient conditions, which will now play a role.
Grundsätzlich, was ist jetzt eben neu?
So, what is new? Well, firstly, you have an undefined cycle on the road. That's new. And with very broad boundary conditions. And because of this, three key changes have to be noted compared to the previous method. So, ambient conditions or environmental conditions, these are new. So we have to take a much broader view of that. It also includes the cold start now, which is important when determining the limits. And secondly is the variability, so you lose repeatability, which is, of course, key for any development effort. Engineers need to have a goal towards which they can work. So if you compare road drives, for example, they will look different each time. So they are now pursuing a moving target, which makes the task far harder. And as was said, this is not the only thing. There's also, of course, the better coverage of the engine map, the wider coverage, which will make itself felt. So it's a change of paradigm, really. In all ambient conditions, the engine has to work fine and has to be clean. Transient behavior, we heard about that. This will be much more at the center of attention in order to pass the test. And then emissions and drivability too. The two cannot really be separated as clearly and as easily as was the case in the past. Now, if we look at what happens, there's base calibration. Now, this is about looking at emissions and fuel consumption and CO2 and balancing them. So there's a steady state measurement that's done for this base calibration. Based on that, there'll be the transient calibration, which tries to achieve the trade-off with drivability requirements. And thirdly, there's the ambient considerations, temperature, humidity, things like that. So here too the goal is drivability and performance.
Wenn wir uns jetzt nochmal das Thema Emissionen jetzt hier etwas...
If we look at efficiencies, or emissions, pardon, what we're still doing today when it comes to test vehicles and testing them on the road, there are certain measures in order to make the whole testing process more efficient. And when it comes to front loading, certain things when it comes to the powertrain, the engine test bed or component test bed, so it can be brought forward, in other words, even to the very beginning, simulation. So, as you can see, several things can be done in order to make the process more efficient. So, the question as to why we need RDE on a test rig on the dyno, because it should be carried out on the road, as was said. Well, the problem with the road is that every RDE drive will be different. You cannot predict from the start what the weather will be like, traffic conditions, driving styles. So each RDE drive is going to yield different results. And if we transfer all this to the test rig, then of course you have the advantage of repeatability or reproducibility, which is very important, and different influencing factors which can also contribute to the overall emission result can be rendered visible much better by varying different factors on the test bed, for example. You can, for example, try out a different driving style, defensive or aggressive, and look at what the impact will be. And finally, on the test rig, by using different kind of measurement equipment, mainly, of course, emission testing instrumentation, you get a much more accurate view of what happens in the exhaust train. Engine out emissions, for example, and also tailpipe emissions can be compared more easily and analyzed better. So my message at this point is, yes, final validation is for the road. That will also be the case in the future. Also homologation will happen on the road. But a lot of these things, if you choose the right methods, can be done on the test stand, and also the calibration. Now, if we look at the development process from the left, simulation, component development, then up to the different development environments, with increasing degrees of real components which are being used, culminating in the road, of course, then it doesn't end with type approval. Rather, we are also checking in service conformity. So it's the regulator who does that. By carrying out random checks, they want to make sure that vehicles are still in spec across the entire life cycle. So if we think about front-loading, this will mean that the more you can bring RDE forward, the more you will be able to simulate. And we've got 4 important use cases. There's RDE, then the road test, which, as I said, can also be designed and planned more efficiently. And if you then look at the test rig, well, there are 3 different use cases, as we said. The first use case would be the simple reproduction of one RDE drive. Now, this may only make sense to a certain extent, because this one drive, of course, does not tell the whole story. But it can make sense to use it anyway. For example, if you've identified anomalies during the test bed, to also have them there on the test rig. Then use case 2 would be RDE cycle test, so using relevant RDE relevant test cycles. So that would be dynamic operation and ideally also a most relevant cycle, which well summarizes the most emission critical states which have been captured somewhere. Now, if you carry out complete RDE drives and if you have situations which are non-critical anyway, that will make the whole process more efficient. Then thirdly, you could do a kind of emission prediction as part of use case 3, virtual testing, which already works quite well and is very helpful, but I'll return to this later. Now, then RDE. One RDE drive is not really telling the whole story, as I said before, which is why it's all the more important that you also analyze this statistically. So a state which you've identified somewhere, is it really relevant if you look at the bigger picture, for example, or is it just a one-off? Now, as I said, if you're analyzing fleet data is also very important. Now I'm going to show you some important results as we see them in RDE. Now, the first one is from Bosch Engineering, which was introduced this year at the Stuttgart Symposium, where the key message was, and I'm not going to address the details here, that on a dynamic engine test bench, which is equipped with virtual technology, we're able to identify a lot of potential for shifting a lot of the tests away from the road to the engine testbed to shorten development time from 240 to 240 or so. And the second important one is, well, something that was introduced at a symposium in Wiesbaden by JLR, Jaguar Land Rover, and AVL together. And we showed something quite similar. So on a powertrain test rig, we were able to achieve similar synergies or efficiencies. Now, it was a fast cooling process that we looked at, so artificial conditioning of a test body to an initial state. So that way we were able to do a lot of cold tests, one after the other. So if you do all this on an emissions dyno, for example, and wait for the whole setup to cool down again, you cannot really carry out 2 tests a day. So on this dyno, we were able to carry out up to 21 tests. Now, this one here has to do with calibration on the test rig. BMW Steyr talked about this at a symposium. It's to do with efficiency on the engine test bed. Now, an application engineer, bottom right, has a task. And he's confronted with a complex system. There's a lot of automation. There's an application system. This could be ETAS Inca as the interface to the ECU. Then an indication system to measure the pressures of the combustion process, and a calibration or optimization system, which sees to the optimization and data storage. So it's pretty complex. And there are a lot of different experts, of course, who are involved. And it's quite hard for the calibrator, really, to agree on all this with all the other actors here, stakeholders, to cover everything. So BMW Steyr and AVL together have produced an approach which has really enhanced the efficiency, especially when it comes to data matching, to bring together data better. It's also about performance, for example. If you do transient calibration, it's all about fast interfaces and between the automation and the ECU. This was done here, of course, by the IT department. Now, all of these are things which you can read up on, well, at this link, which is also on the chart if you're interested.
Das Thema transiente Kalibrierung.
So when it comes to transient calibration, perhaps I can briefly touch upon this. Now, there was a talk on that too in Wiesbaden. Now, what this is about, with your classical DOE approach, you talk about steady-state points, but once you progress to transient calibrations, it's about time progression. So they now have developed a method, as Tippen has shown, that these time progressions can be translated into scalar KPIs, as it were, and the same method can then be used that was also used in steady-state tests. The advantage of this approach is that the same method, or that a normal application engineer, with the help of, can use this method, working very quickly, without having to think or consider other innovative processes. Now, this is quite a stable process now, and it has really improved transient calibration considerably. Finally, and this too has already been mentioned in a previous presentation, the virtual engine or virtual engine test bench. Now, our task was to do an ambient calibration using non-standard conditions, so altitude, temperature, which you'd normally do in a climate chamber, which costs 2,000 euros per hour or so for testing. And perhaps, this is done in Granada or in Sweden, which involves an effort too. Now, we already use a method now where we can do the whole thing on a virtual test bench. By the way, this was a cooperative effort together with ETAS. So the ETAS lab car now has been incorporated into a system. So we set up the engine test bench and well, transferred it actually to an office. So the only central device was a control unit. Everything around it was simulated. So all the ambient factors and the engine itself too. And we carried out different correlation tests. So here, for example, in red, you can see the measurements on the virtual test bench, and in black, you can see the associated vehicle measurement. And already this picture shows you that we're operating in a pretty good range, only 3% deviations when it comes to NOx emissions measured. Now at AVL, we implemented this. It's called Virtual Test Bench. It's based on a co-simulation platform. So all the simulation models, of course, need to work together, play together. And we do have a product for that. It's called Model Connect. And something else that I could or should mention here perhaps is that we also have a solution in order to really transfer these models to the engine test bench by a system, or with the help of a system called AVL Testbed Connect. And the different models can then play together in real time or not in real time as needed. So, and with that, I've already arrived almost at the end of my talk. Finally, let me give you a summary. RDE is an important driver for front-loading calibration tasks into earlier stages of the development process. This makes sense. It's also a must, because otherwise we cannot possibly extrapolate the complexity of the road situation. And it's done by using appropriate methods and tools which are already well established. There are a lot of reference projects which deliver excellent results. And finally, another point, yes, this seamless interplay within the RDE tool chain is very important indeed for the whole approach to become accepted. It's important that the effort is not too high. And another thing I should mention are the organizational structures that need to be in place at the OEMs. Some of them still have big hurdles ahead of them.
The key area that we wanted to talk about today was what we've been doing recently for ASCMO, how we use ASCMO at Mahler Powertrain. So we've been using ASCMO for over 4 years now, and primarily I think we've been using it for a slightly different use case than certain other companies or how it's been designed for. So rather than purely on the calibration side, we've actually taken it onto our development test beds as well. And over the last 4 years, we found it's become really instrumental in providing the ability to model complex systems with a very high degree of accuracy. Some of the examples that we have used it for in the past are whole area map optimization, cold start optimization, PN optimization. So this is also for single and multi-injection concepts as well, so both GDI, gasoline. We've also enabled investigation into transient load step optimization as well. And finally, one of the very interesting parts was a model for dynamically investigating complex valve train systems. So this was for one of our customers, a CVVL system, so in the same vein as a multi-air system and from Fiat. So we've proved internally for us it's very, very useful for our development programs. And what I wanted to talk to you all today about was how we are using ASCMO to help reduce PN or improve our PN optimization for legislative cycles and also for RDE development as well. So RDE optimization, it really is a hot topic. I think the RDE requirements and the issues that the industry is seeing was really described very well by the previous presentation, so I won't dwell on that too much. But really, the key area of interest for me is really how can we front-load development programs to meet RDE legislation. So here's a very simplified model of a new engine development program. So you sort of commence with your vehicle targets that get fed down into your powertrain, going to simulation, move into engine development, and then back up through when you start engine cycle simulation, vehicle cycle testing, and now on-road RDE development. And what we really want to do at Mahler Powertrain is try and integrate vehicle simulation across the entire engine development program. So rather than just performing emissions development in your latter stages, once you have your engine on a transient test bed, or in a vehicle, or on a vehicle on the road. We really want to bring it forward to see what we can do for emission simulation, really with a view to reduction in time for a program, reduction of the cost to our customers, and also efficient utilization of our resource as well on site at Marler Powertrain in Northampton. So the key point that I want to discuss about there, we've taken just a subset of our RDE development. So we want to show how we can use RDE, or how we can use ASCMO to support RDE simulation when we are, very early stage in a program. So when we've just completed our simulation, and when we've got an engine very early stage on a test bed, so potentially without a torque structure, so we're not in a position to start transient optimization yet. So what I'd like to do now is just hand over to Matthew, and he can start talking to you about how we've actually optimized our ASCMO models at Marler Powertrain.
Morning all. So I just wanted to go into the background of how we've traditionally done PN optimization at Marler. So we've got a set task. The task might be to assess different injector options and determine which one's most likely to enable us to achieve our PN targets. Typically what we've been given is a series of sites, and these sites have been determined to be high importance on traditional legislative cycles. And what we do is we do a series of maybe SOI sweeps, rail pressure sweeps, kind of 2D, 3D sweeps to try and work out which injector option would be the best, and whether actually these injectors would enable us to be below our cycle targets. So we'd make our injector option based off that, our injector option decision based off that work, and then sometime later we'd be able to do cycle testing either on a dyno or on a vehicle. And at this stage we might be lucky and our PN might be okay, which would be great. However, there's also a possibility that your PN would be an issue. And at this stage, it's identified quite late in the program. You've then got to go all the way back to the beginning and try to investigate, potentially working with suppliers to try and get other injector options which might help reduce PN further, or maybe looking at alternative strategies as well. So what we're suggesting, our method for using ASCMO is try to model the cycle PN much earlier on in the program. So by using a whole area data gathering exercise using a DOE, we'd then be able to take all that data, feed it into ASCMO, and create PN models, which will enable us to kind of not only work out what the cycle PN is, but also we found that ASCMO offers a brilliant environment to be able to see very complex multi-dimensional systems in a way that we just couldn't do before when we were just doing 2D and 3D sweeps. So then we take that ASCMO model, we feed this model into CarMaker, and this is used to assess all these different injector options. And then if we have a PN issue now, we've identified this in a simulation phase, and we can go back to the beginning and we can start looking at alternative options, trying to make sure we stay below our engineering targets. If our PN's okay, we've then made an injector option decision based off the cycle rather than the kind of the individual site targets. And interestingly, going through this method can actually deliver a different injector option to what we've derived through the alternative method, just because you're considering the whole cycle rather than each individual kind of point, maybe 10 points, 10, 15 points that we do traditionally. So now our PN issues identified much further. When we go into the cycle testing, we have a much higher confidence now that our PN will be okay. And of course, there could still be a PN issue. That's always a possibility. Just going over the model that we've used here as the example. So it's a steady state DOE model on a sub 2 litre gasoline direct injection engine. And we've typically found that around 1,000 points would be enough to kind of get the kind of PN model that we'd need to for this work. We use an automated test approach, and it takes around 2 weeks to gather this type of data. So kind of within 2 weeks, we can model each injector option much quicker than we had previously. And the important thing that we found is by adding coolant temperature and plenum temperature into our model enables us to feed that into cycle simulation software. So we found that ASMO has been great at kind of offering us the ability to kind of constrain our data and how we collect that on the test bed. So the simplest one would be just a speed load constraint, which enables us to kind of cut off the run-up line section, but also more complex ones, such as the one we use for kind of cam positions to kind of focus the DOE in certain areas, or actually cut off the data acquisition in areas where we might have issues such as pre-ignition potentially. And other ones that we have are things like the maximum allowable overlap with kind of load-based formula, and this is just to kind of prevent the engine from experiencing heavy misfires or instability. And kind of all these constraints that we add just help to improve the data efficiency and the data flow that comes off the test bed. It's been really useful. So after we've collected all this data, the data is then fed into to ASMO, enables us to build several models. So we've got fuel flow, BSFC, particulate number, emissions, pumping, a whole host of models that we use to analyse how the engine's performing. So taking BSFC as a pretty good model, it's good. We've got a good R squared here. The root mean squared error is pretty low. And as you can see, there's only very small percentage errors in each area. You don't have points where the prediction is predicting very high BSFC, but actually modelling a low BSFC. So kind of trying to come up with an optimum solution for BSFC for like minimising cycle fuel flow is very easy using a model like this. However, if we go to the kind of the PN model, we've got R squareds of 0.77, and it's a very poor model. And we also have the problem is if you look on the x-axis predicted PN flow and the y-axis is measured PN flow. In some cases we predict very low PN, but actually we measure very high PN. So this is obviously an issue when we're trying to optimize PN. And kind of the main reason for this we found is kind of, which many people have also observed as well, is kind of the repeatability for the measurement of PN. On the x-axis we have the SOI timing, on the y-axis is the PN flow numbers per second. And we've done kind of numerous sweeps here. We've got 4 sweeps, and every single time we've done it, we've had a different result, and also we've had a different nature in the kick-up as well, which is obviously quite a problem when we're trying to minimise PN over cycle. So because the PN model is so poor, it's important to try to validate this result, and at least to see if it's useful for still driving optimum. So what we've done is we've used ASMO, and this is fed back to us that for each site, coolant temperature, SOI, and rail pressure are the most important factors in PN. So what we do is we go to a series of sites over the operating range, and we sweep SOI, rail pressure for different coolant temperatures, and to establish kind of the reliability of the model that we've gathered.
Once we had the model from Matt's team, the task then for looking into the RDE assessment was really to assess the performance of the 2 different ASMO models from the 2 different injector sets. What we wanted to try for this example was really to see how we could link ASMO to vehicle simulation software to really try and optimize the very early stage RDE development, to really investigate the emissions for PN and, again, BSFC. Why would we want to do this? Well, really, I think the vehicle simulation is a very powerful tool to enable optimization of these ASMO models and understand to cover the entire RDE operating space in the simulation. So we can have full powertrain models inside the simulation. You can also weather effects such as temperature and wind, road curvature models, and also different traffic effects, gradient effects from the road that you're driving on, and also different driver models, which is one of the key aspects that we found, and also then the effect on vehicle dynamics. So if you change your vehicle but keep the same powertrain, what effect would that have on the overall RDE results? So to integrate ASMO into CarMaker, it was quite a relatively easy process. So it's all performed by the functional mock-up interface. So we could export the ASMO model as an FMU, and that FMU is then connected directly into the CarMaker simulation environment. So how they link together really is quite key. So the signals that CarMaker provides back out to the ASMO model are engine speed, BMEP, intake and coolant temperatures, and then ASMO is then used to calculate the intake and exhaust cam, SOI and rail pressure. And then the ASMO model then predicts from all of that information the PN and BSFC for all the RDE simulations that are passed to it. So then really for us, I think whenever we're doing any RDE simulation, the key is really a very good design of experiments for your RDE testing. So at Marler, we've developed some bespoke solutions for the vehicle simulation. So the first of those is the RDE routes. So we've digitized 10 different RDE routes in the UK and Europe. I've got one example here, which is just a very short section, which I'm going to present data from for the rest of the presentation. So it's 5 kilometers from our site in Northampton. So it's one of our certification RDE routes. So the key benefit of showing this data is then in the future when the powertrain is in a vehicle, we can then validate back to our simulation as well to prove the entire loop. The next point, and I've mentioned it before, is driving style. So that's for RDE, we've got a very high range of driving styles. So that, for those of you who are not too experienced in RDE, so this is one of the metrics for trip dynamic measurement. So the red line on the plot is the upper threshold, and then what we've got here in blue is our simulated output from the different driver models that we've generated at Marler for our vehicle simulation, and then the red is measured RDE data performed on that route. So it not only encompasses the RDE region, but also real world driving as well, so how drivers could potentially drive that route. So for this simulation, it's quite interesting to go over and above the RDE requirements for an engineering factor of safety. And then the other aspect that vehicle simulation can provide us is then also the effect of different traffic situations and also different road furniture as well, so different stop times across your RDE cycle and also different speeds whilst you're progressing through your RDE cycle as well. So really for each injector type, we performed over 160 simulations for each of them. This really enables us to understand how the injectors perform over a full range of RDE conditions. So if you just consider how that builds up, you can see you start multiplying up your different vehicle models to your different drivers and also to your different routes as well. So you can start obtaining a really huge matrix of different test requirements, which is where, if you try to do this on a vehicle on the road, you're looking at a year and a half to really achieve that. But then within simulation, we can achieve this within hours, if not days. And with also the vehicle simulation as well, we can really get key, we can have very detailed outputs which are not dissimilar to the outputs we would get from a piece of PEMS hardware as well. So we can then see, so this plot here really shows the outputs from a number of different drivers, going from our defensive driver all the way through to the aggressive driver with a couple of different traffic scenarios as well. So you can see how the vehicle speed changes over those first 5 kilometers, and then you can see how the ASMO model then responds with providing a different PN response from those different driver inputs and road simulations as well, or route simulations. So what that gave us was a number of different results. So we've got in blue, we've got the results from injector 1 over the first 5 kilometers, so the very early, or the cold start section of the RDE cycle, and in red, the bottom plot is then injector 2. So then looking at these results, these are all the different, inside these shaded areas are the different 160 different cycles that we ran. And the key point is that we were able to pick injector 2. We showed the benefits of injector 2 very quickly over the RDE cycle, so they enabled us to help making the decision to pick that injector to move on with the thermodynamic development. And I think the real key points that we want to take away from this is to say that the results were able to be passed back to the development team within hours, and no testbed cycle simulation time was required for this this simulation. Also, we were able potentially to compress the development program as well, which is a real benefit for our customers. So just to really summarize how I feel that these simulations can benefit RDE development in the future. So we can assess many different RDE simulation requirements in a very short time scale, so 160 routes in less than 5 hours. We do get a high confidence in the model output because the ASMO model is based on real measured data from the engine, so there's a high degree of confidence there. And we've got a wide spread of RDE test results as well. And then the key final point is, again, resource utilization. So we can really perform the simulation in parallel with thermodynamic development. So we're not spending time on a test bed to do this. The test bed can carry on doing additional work. It's performed upfront and very early in the development program, and then there's no requirement for any vehicles to perform the test at this stage as well. So then you've got the added benefit of potentially reducing the number of prototype vehicles for your development program. So then, I think as we've discussed already, there's further work to be done. A steady state model is not the complete answer, so now we're investigating the implementation of Mocha to try and pull together multiple ASCMO models. So with a dynamic ASCMO models, with our steady state ASCMO model, and then also warm-up strategy models as well inside ASCMO to really pull together what could be very detailed emissions RDE simulation for this engine. And then also we're going to include a catalyst chemical model, so not just look at engine out emissions, but also have an investigation of what the tailpipe out emissions to be, to then compare against the legislative targets for RDE. And this is all happening very early stage, so I'll give a very high degree of confidence to our customer on this instance. And then the next two stages are really then to correlate the simulation results to the transient testbed, and then the next stage after that will be then correlation on the Marla Real Driving Emissions Centre. So the Real Driving Emissions Centre for us is a key point. I think I've talked a little bit too much about ASCMO products, so on ETAS products. I want to do a little bit of Marla marketing, if you will. So this is our Real Driving Emissions Centre. So this is going to be operational in Q2 next year. It's already being built. It's the outer shell's ready, or the outer shell has been built. So it's a full vehicle altitude chamber, so we can run. So it's a whole vehicle. So it's not just an engine simulation, just a gas in, gas out simulation. The whole vehicle will be subjected to the altitude. So it's from zero meters at sea level and go all the way up to 5,000 meters, and at the same time fully climatic from -40 to 55 degrees C positive. This really highlights quite how key we think RDE is for the future, and it's going to enable us to really perform RDE from simulation all the way through to final validation from our site in Northampton. So it's going to be a very powerful tool. And if anyone wants more information on this one, please let me know. So that's everything we wanted to talk about today. So I'd just like to thank you for your time and listen to myself and Matt discuss what we've been doing with ASCMO at Marla Powertrain.
In my presentation, I will focus on a tool chain, so actually a platform that we have developed at Toyota Motor Europe in order to validate and optimize real-world emissions. So currently, if you look at the top of the slide, a lot of the calibration work is still done in the testing vehicle and on the roller bench. So in that case, we need several optimization loops in order to satisfy all the criteria. This is quite time-consuming. Therefore, the target of this tool chain was to simulate the real-world emissions in all kinds of boundary conditions in order to connect this in a later phase also with some auto-optimization tools in order to optimize and validate the calibration virtually, in order, of course, to front-load the calibration activities and to reduce the number of testing that we need to do. So today I will mainly focus on this tool chain itself. Here on the slide you can see what is basically our target. So for any route which we can select on the map, we want to predict what would be the relevant real driving emissions and the conformity factor. In order to do this, we have connected a lot of different models together. The first item that we developed is a so-called offline driving profile generator, which is based on machine learning techniques and which gives us the possibility to get a realistic driving profile for the road that we have selected on the map. And this information is then sent to an online driver model, which is connected in the Simulink-based tool chain. Additionally, then we need to integrate an engine model. Of course, the engine control unit model. Then also the one-dimensional engine model, for which we have used GT Power, including a vehicle model. And finally, connected to the engine model is an ASCMO dynamic emission model, which predicts the engine out emissions before these are sent to the catalyst model. So this is quite a complex tool chain, but we need all these different factors to have an accurate simulation. And finally, we can simulate what would be the actual real-world tailpipe emissions. So then I will go a bit into more detail in these dynamic ASCMO models which we have used. So I think we can differentiate two types of these Gaussian process models. We have the static MBC models on the left, for which we usually need to make a DOE test plan, which takes quite some time to measure on an engine bench, some weeks. And usually we have many inputs, usually many calibration parameters, and that we use finally to optimize the base maps of the engine calibration. On the other hand, there is a dynamic MBC, which I will talk today about, which as a training data can use any kind of dynamic data from either an engine bench or a roller bench. This data recording takes much less time. That's a matter of just a few hours. We use less input parameters in this case. And of course, in order to train in the bench, we need an engine which is available with already a reasonable maturity of the calibration. However, we wanted to try this tool. We thought it had some potential, but we were not sure what would be the accuracy in the very dynamic RDE driving conditions. So initially, we did some experiments on the engine bench. You can see on the left. So we were modeling the NOx emissions and comparing two measurements. We trained both a static MBC model and a dynamic MBC model. And as you can see, when the cycle is getting more harsh or more dynamic, basically we lost accuracy, so we had an increased gap with the measurement of the NOx emissions. However, with the dynamic MBC model, after just 2 hours training, we could get a very good accuracy in RDE conditions. Then in the next phase, we wanted to further optimize this model. And we had a look into which input parameters are most relevant and gives us the best accuracy in order to simulate RDE emissions. And in this example, we trained the model by a 2-hour RDE cycle that was trained on the bench. As you can see, we can use a very simple model approach like on the left, in which as inputs, we just use the engine operational inputs, which is the engine speed or the injection quantity. But when we add more physical input parameters to the model, like the EGR or the intake pressure and temperature, you can see that the prediction accuracy for NOx is further improving. And in our toolchain, we have these physical parameters available because we have coupled the dynamic ASCMO model to the one-dimensional GT power model. So we have selected these inputs that you can see on the top. And in this case, we trained the model with just over 2 hours of training data, which was a kind of harsh, so very dynamically driven RDE cycle, and also an NEDC, which covers the more steady state and smooth driving behavior. And we predicted another cycle, which is so not in the training data, WLTC. And as you can see here, the predicted engine out NOx and the measured engine out NOx are correlating very well. The same for CO2, slightly less for CO and HC, for which maybe there are not enough physical inputs available to the model now. However, this was judged enough to integrate in the toolchain. Then in the next phase, we have measured some on-road RDE tests and also some WLTC tests in this facility, in order to check if the domain that we trained, is it wide enough to cover real on-road conditions in different circumstances. And so we made a special focus on checking if the training domain actually would be wide enough. So you can see on the top right in black, basically this is the training domain from the 16 hours of data. For the engine operation, below also for the gradients of engine operation, which is very important to take into account for training dynamic models. And also for the physical inputs, as you can see most below, basically the black training area covers very well the different on-road and chassis dyno validation tests. So in the next phase, we have validated, so we trained the ASCMO dynamic models with these 16-hour data. In the first step, then, we validate the emission models itself. So we give measured inputs to the model and compare the measured versus the predicted emissions. In this case, this is an example for NOx emissions in an RDE cycle at higher altitude at around 6 degrees. And as you can see in both second by second traces and the cumulative emissions, we could get a very high accuracy. So the cumulative NOx for a variety of different cycles in different environmental conditions was within plus minus 5% accuracy. Then in the next phase, we have integrated this dynamic ASMO model into the tool chain. That means that in this case, the model gets all inputs not from measurement, but of course as predicted by the 1D engine model. In combination with the driver model and the engine ECU model. You can see here an example again for NOx, which is still almost within the plus minus 5% boundaries. So the next part of the presentation then will focus on the human-like driving profile generation, which is very important for RDE simulation. So, of course, we can select a route on a map and try to predict the emissions. And from the map, we might know what are the maximum speeds in all the roads present in this route. However, of course, we know that in real driving, the vehicle is not just following the maximum speed target, but actual things are happening on the road, and we have traffic lights, speed limits, roundabouts, stopping points, and so on. So the target is here to predict what would be a typical driving in this route. Therefore, a new methodology was developed. We need, again, a training process for this methodology. You can see the result of this kind of training on the right. This is a bidirectional map. This is a two-dimensional map, which is based on the TSNE algorithm. This is basically an advanced way of clustering multidimensional data into categories with similar characteristics. As I said, so we need to train this BMAP. This, on one hand, is done by recorded human driving behavior. That means actually measurements in the car, how the driver is operating the vehicle, what is the resulting vehicle speed. At the same time, of course, the GPS data is recorded. And from the GPS data, we can connect to a geolocalization database, like here, or Google Maps, or any other provider. And we need to extract the driving context. So that means, what are the typical characteristics of this route all along the route profile? For example, the slopes, speed limit, corner angles, stopping signs or traffic lights. These are, of course, many different dimensions. And finally, we want to correlate how the human is driving, how he's operating the vehicle based on the visual input he sees from the road. So he sees the stopping sign, so he is expected to stop. And this correlation we want to train to the model. And finally, so we end up with this bidirectional map, in which every point basically is an histogram of probability. In this case, you can see different clusters of training data representation. And the color differences here show the different speeds. So in this graph, for example, we can quite easily compare. We can see the clusters based on speed. But we can, for example, also see, for example, when there were stopping signs, we would get another color distribution. So in the next phase, when we want actually to predict driving profile for a route, we have to follow this process. So first we go to the map itself, we select a route, then we connect to a database like the here database to extract all the route attributes. And finally, all these attributes, which are 9-dimensional data, are projected in the BMAP. And there will be made a weighted average of nearby BMAP points, of histograms basically. And finally, we can make a z-score band, and through an inverse function, we can derive what would be statistically, in this kind of combination of route attributes, what would be a representative speed. And this is repeated for each segment of the route. And finally, so we have a new profile of the route that we can simulate and estimate the actual RDE emissions. So this was a validation example. So we have trained this driver model with a lot of data. And then we try to predict a route that we have selected on the map. In this case, it was somewhere in France. Of course, this route was not part of the training itself, so it was purely predicted. We have run this in the tool chain, so we know also the vehicle operation, the axle pedal operation, and so on. And then we have compared it to a single measurement that we have done on this route. Of course, statistically, you would need to run the same route maybe 100 times, and every time you will get a slightly different result. But we wanted to check, as a proof of concept, does it really work? Can we get a realistic driving pattern compared to somebody really driving on this road? And you can see some of those results on the right of vehicle speed, gear number, how the axle pedal is pushed, which of course is one of the outputs of the tool chain, and also what is the distribution of axle pedal. And this is matching quite well to when we actually would go there to measure on the road these characteristics. So finally, some conclusions. When we optimize real-world emissions, we really need to go at least some part of the process to virtual development because there are so many different combinations of environmental parameters that we cannot test them all on the route. And we found that the use of dynamic MBC models is very beneficial, since with limited training, we can get quite high accuracy to predict these emissions. And to go to fully virtual simulation, so it's important to have also good driver models, which are able to predict also new routes without needing the possibility to really go there. So how we want to use this finally in the development. This specific example was done for a diesel engine case, but of course also similar process can be applied for gasoline and hybrid vehicles. So basically we can select any route that we want on the map. Thanks to the virtual driver, we can get realistic speed, shift traces, and of course the altitude profile of this road. Then we can run this in the tool chain for RDE emissions. That means we can get, of course, many outputs of this tool chain because we have an online driver model. We have all the engine information. We have all the engine control information because this is also recorded. And that means we have enough information to do virtual RDE validation and to replace at least some of the real tests that would need to be performed to get enough confidence in the calibration. And of course, we can use it then to find critical events along the route, which need a special focus and which might need some further improvement of the calibration.
Interesting presentation, excellent. The last element, the exhaust gas catalyst models, you didn't say so much because I think this is the Champions League of exhaust gas modulation. So the parameterization, how sophisticated is it?
Yeah, so actually for the after-treatment models, we have used AxiSuite models. These are, of course, many catalysts behind each other. There's DOC, DPF, SCR catalyst. This is takes some time to calibrate these models. They are calibrated based on synthetic gas bench test. Luckily, in this case, we had a kind of database inside Toyota with already calibrated models in aged condition. We did also the validation of the catalyst models and the urea dosing strategy. So we have measured this on the road and then compared to, let's say, this submodel validation results, and they match quite well also in dynamic condition. Of course, SCR models maybe theoretically are more simple models compared to NSR models or maybe gasoline models, but basically this works quite well in a simulation environment.